Hello, hi, welcome back. All right, so we're going to continue with chapter 3, which is on linear regression. Yeah, the whole set of this week's lecture going to be on regression actually. So we're going to start a little bit on linear regression, and then it's going to move forward towards to multiple regression and etc. Okay, let's look at it. And so before we proceed, right, I would like to show you the bigger picture, right, and also the package that we're going to use to run this regression. Okay, so we're going to use a famous package called scikit-learn, right? Scikit-learn. This is in fact a link. Yeah, if you click on top of it, it will take you to the website. So have a look at this. So I have actually took this picture from this website. Okay, now let's see. Okay, now we start here. All right, we start here. Then you have more than 50 samples. If you don't have more than 50 samples, you are advised to get more data. All right, so if you then your data in the form of category or not. By now you know category simply means your data set in the form of classes. Right, so if it is not in the form of classes, then it's going to be in the form of numbers. If it is no, you're going towards this or your right hand side. Whereas if your data in the form of categorical data, of course you go to your left hand side, and your data is labeled, then you can do classification. Yeah, so you have your data set, you have your labels, you can push into machine learning classification method per se to do all those machine learning tasks where the predictive model end of the day it will tell you what class your new data is. Whereas if you push it to your data is not, data is not, that is no label, then as I told you, you're going to now push it to clustering method. So here clustering method, what it will do for you, it will create a structure. It will show you the number of groups, the number of clusters in your data. All right. Whereas for classification is a supervised machine learning, whereas clustering is unsupervised machine learning. Okay, that is on your left hand side. Of course, as we move into each method, we will look at a number of different classification method, different clustering method that we can move, and then we can do models with. Whereas on your right hand side here, of course, your data in the form of a numbers, then you might want to do regression. That so the next few slides is going to be on regression. And if your data set, let's say now, if your data, the predicting quantity, right? Predicting quantity. So we want to do that actually for regression. Whereas just we want to look at the data, you might want to like reduce the dimension. Your data set in a very high dimensional space. For example, your data set has like 10 columns, which is we call as features now. 10 features. You can't really visualize them. So rather what you will do is that you reduce to lower dimension, for example, dimension 2 and dimension 3, in order to see the pattern or the structure of your data. So we can do that with dimensionality reduction methods. Okay, that is in box number 4 on your right hand side here below. Whereas on the regression side, we will try to estimate. Yeah, that at the end of the day, our target will be numbers. So end of the day, we predict number, right? For example, the temperature of the day, right? So these are the things that we are going to cover in this course, in fact. And let's move to the first part, regression. Okay, so regression is going to be the first part. Then we are going to do classification, then dimension reduction, and then clustering. Okay, this is how the course of the structure is. Okay, the structure of the course, right? Okay, sorry. Okay, first part, the simplest is linear regression. By now you know that given a set of points, at this points can be any dimensional space, but what you're trying to do is that you're going to try to fit with a hyperplane. For example, in two-dimensional space, just a two-dimensional data set. In fact, this is just one-dimensional. You're just going to fit with a linear line, a straight line, which mimics the pattern of the data. Okay, that's in short. Now, the goal of linear regression is to model the relationship between one or multiple features. So these features we also call it as explanatory variables, and with a continuous target. Okay, so continuous target. So continuous here simply means a real number, right? Yeah, so the target, you know by now, what is the target? The target is the value that we are trying to predict. Okay, and then in contrast to classification, yeah, so we always try to compare with classification. In contrast to classification, regression analysis aims to predict outputs on a continuous scale rather than categorical class labels. So for classification, yeah, we are trying to predict the class labels. Whereas for regression, we are trying to predict a continuous value. Okay. This is an example. Previously, I talked a little bit on California housing data set. So this is an example again. You see, if you have like 8 attributes. Attributes again, attribute simply means 8 features. So notch 1, 2, 3, 4 until 8 features, and then the last one here is the target that we are trying to predict, the house price. Okay, and then these are instances. House number 1, house number 2 until how many number of houses? We have what, 20,640 number of houses data set. Okay, now of course when we can, there are these data are well-known data sets, so some packages carry with it where we can just straightaway download to our Python notebook and look at it, do some, okay, here we will do a regression on top of it. Okay, now linear regression. So when you look at, you can just get it in your Python notebook. You look at the data. For example, so of course they will explain to you about the type of data and the content, number of instances, number of attributes, predictive attributes, and target. Okay, so now 8 numeric predictive attributes. This is actually, they have 8 features and then 1 target. Okay, so 1, 2, 3, 4, 5, 6, 7, 8 features. You see, there are 8 features, right? Okay, so with median income in block group, median house age in block group, average number of rooms, average number of bedrooms, block group population, average number of household members, block group latitude, longitude, and etc. There is no missing value. Sometimes we have missing values. So during if there is, then you will find a way to either remove it or you will impute it. Okay, all right. Now, so the goal of simple or univariate linear regression is to model the relationship between a single feature, which is called also as an explanatory variable x, and a continuous value response, target variable y. Okay, the equation of linear model, yeah, just like a linear model simply means it's just a straight line. Yeah, so y equals to w0, which is the intercept. W1 is the coefficient of x. X is the so-called explanatory variable, or we call it as a feature. So if we have one feature, this is the equation that we will use. Previously, we had 8 features, so we might end up using a multi-regression, but here it's just one. Okay, all right, so how do we do it? Basically, our job is to find a suitable W0 and W1 such a way that the given points will be the given points will be very close with the line that we are trying to draw, right? So the method is also known as ordinary least squares or linear least square method. Okay, there are many ways actually, but this is one of the easiest way to do it. Okay, so by looking at this picture, you can I mean, you can figure out. It's actually basically the idea is to find the right W1 and W0 to fit with. We're searching for a suitable W0 and W1 so that we can reduce all these residuals. Right? The residual simply means is y hat. Y hat is our predicted value. For example, for this point here, this is the y value, right? Whereas our predicted value y hat is this value here, okay, on the line, okay. All right. So that's what we are trying to do. We want to reduce all these residuals. So the goal is to find the weights of the linear equation to describe the relationship between the explanatory variable and the target variable, which then can be used to predict the responses of new explanatory variables that were not part of the training data set. Okay, so we actually have an objective function. Yes, objective function which we would use to reduce this residual. Okay, so the objective function usually would be a cost function. Which will calculate difference between the predicted value and actual target value. So we have a cost function. Based on this cost function, we want to reduce the residual. Okay, so one way is by minimizing the sum squared error. Yes, the sum squared error geometrically represents the vertical distances to that sample data, which I have been calling as residuals. Okay, so first is the loss function. Yeah, the loss function computes the error of a single training sample. Okay, so L, the loss function, L is the loss function with the two arguments W0 and W1. So basically, it's W divided Y minus Y hat. Yeah, Y is the real number, the original data set, and Y hat is the predicted data set which falls on the line, and it's squared. So Y hat, in fact, is the equation that we are trying to fit. Whereas the cost function is the average of the loss function, average of the loss function over an entire training data set. So this is the equation on top actually. So what we did is that we sum it up and we did divide by n, and represents the number of points that you have in your data. So n is number of points, or we are now used to calling it as instances. Okay, so again, the subscript is not a power of xi, rather the subscript refers to a different training, each point, different training samples. The training samples are the points actually that you are going to give to the regression model to make that the fitting. Yeah, this equation here. Okay, the cost function is similar to mean squared error, one of the regression evaluation metrics. So we are so used to using this mean squared error actually. Okay, sometimes we have an extra term here, divide by 2. Yeah, so but it's not going to. It's just that sometimes it tend to we get the accuracy faster. Sometimes it might slow it down, right? As long as the cost function that we are going to use is differentiable, which means continuous. It doesn't break in between, and also convex. Yeah, it's not concave, convex. Okay, a simple yet powerful optimization algorithm is called gradient descent. It's very famous. In fact, most of the artificial neural network using this method to improve the next accuracy for the next iteration. So as we move further and further, we keep on improving the accuracy such a way finally it reaches to the best accuracy. Again, you can relate to Newton-Raphson method. Newton-Raphson's method, yeah, to find the root of a given equation. Yeah, numerical method to find the root of a given equation. So it's somewhat similar. We're trying to find, using the gradient, we want to go down there quickly, such a way that we reach to the global minimum. Okay, yeah, we want to minimize. Yeah, the idea is to minimize this error. Okay, that would be the first part of this chapter.